So this question is about second order systems. So we're going to consider a second order system represented by a second order differential equation. As you can see, we've got x as being our parameter representing the variable, and a is a scaling factor, b is a scaling factor, and c is a scaling factor. We're first asked to take Laplace transforms, and when we drive this by a unit step, show that the response in the S domain, x of s, is given by the expression 1 over s multiplied by 1 divided by as squared plus bs plus c. Right, that's the first thing we have to do. Then we have to write the response, this response here, in canonical form, so we can identify natural frequency and damping ratios in terms of the parameters a, b and c. Then we're going to derive an expression for the poles in terms of natural frequency and damping ratio. And finally, identify basically, what damping ratios relate to having an overdamped, critically damped, underdamped, and an undamped system, and illustrate what typically these would look like using a sketch. So let's consider the second order differential equation, and we have to take first of all Laplace transforms so we can analyze it and come up with its transfer function. And because we're going to be doing this in terms of looking at its transfer function, we don't have to worry about initial conditions. So the important thing to note is a, b and c are just constants. Second derivative goes to s squared x of s. First derivative of x goes to s times x of s, and x just goes to x of s. And f of t goes to f of s. Then we factorize out the x of s, of course, which is easy because they've all got them in on the left-hand side. And the transfer function is then going to be x of s divided by the f of s driving force, and we end up with 1 divided by as squared plus bs plus c. Now, if we drive that with a step, then our x of s is going to be a 1 over s function, right? So we need to multiply that all by 1 over s in order to get the response. And then we can divide through as we see fit in order to get rid of the scaling factor in front of the s squared. So we've got our transfer function. Now we need to write that in canonical form. So we really need to concentrate on the denominator here. And canonical form is when there is just a unity term in front of the s squared. So we've already got that. In front of the s basically relates to having 2 zeta omega n. So zeta being damping ratio and omega n being the natural frequency. And the constant term at the end is going to be omega n squared. So we can immediately now relate this to what the parameters are. And we know that poles are going to occur of this system when the denominator goes to 0, right? So when the bottom the bottom denominator term goes to 0, the values of s correspond to poles. So that's just what I've said. So we can identify then that c divided by a corresponds to omega n squared, and b divided by a corresponds to 2 omega n zeta, right? So now we need to solve, obviously, the bottom equation to find the poles, and we know that for a quadratic equation, the classical formula ax squared plus bx plus c equals 0 has the solution x equals minus b plus or minus square root of b squared minus 4ac divided by 2a, and you really should know that off by heart. It's so important. And we also know that if b squared, so this bit at the front here, if that's bigger than minus 4ac, then we've got a real solution to the square root. Otherwise, we've got an imaginary solution to the square root. So if we solve this equation now then, which is quite easy, so this is now the a is 1, the b is 2 zeta omega n, and the c is omega n squared. This is minus b plus or minus b squared minus 4, a is 1, c divided by 2 times a, which is 1. And we just have to rearrange that slightly, multiply out the squared term here, we can take out 2 omega n because it's 4 omega n squared in there, so we take that out. And then we can just basically divide through by the 2, and we get what the solution is in terms of S, which is the pole. And we can immediately identify 2 conditions. If if zeta squared is greater than 1, we're going to have if omega n is omega n squared is less than 1, right? If this is less than -1, then we're going to get an imaginary value here. So we're overall going to get a complex result. In which case we can actually say, well, let's just change the order of this and put j in front of here. So just to show that this is a complex number. Always we have plus or minus, of course, with the square roots. So now we need to identify what zeta means in terms of damping. And if zeta is bigger than 1, we've got a real solution, right? And damping anything more than 1 is going to be an overdamped solution, right? So we just look at the solution to the equation. This is going to be positive. This is going to be positive. So this is going to be a real solution. And the solution, and it's going to be overdamped. If it equals 1, then that's an interesting condition because the zeta squared minus 1 goes to 0, so we lose this term. In fact, then we just get the minus zeta omega n term in there, with none of this contribution from this term here, and that's basically means the system is as damped as it can be without having any complex values in there. So it's not going to oscillate, but it's as damped as it can be. In fact, this condition is known as critical damping. If we've got a value of zeta between 0 and 1, then we do have basically a complex number solution, or generally a complex number solution. We certainly have an imaginary part coming in for the second part of this. Consequently, there's going to be a bit of oscillation there. And this condition counts as being underdamped, right? So it's not critically damped, it's less than critically damped, so it's underdamped. Now, if zeta was actually 0, right, the system has got no damping at all, and then we've got a solution which is purely imaginary. And purely imaginary means it's going to effectively be an oscillatory system with constant amplitude. We'll come to that in a second. However, if zeta is less than 0, if you look at the first term, we see that actually goes to a positive value here now. And as a consequence of that, what we're going to have is an unstable system. So, in the condition where we have zeta equals 1 or more, so 1 is critically damped, but more is overdamped, we've just got a solution which is not oscillatory at all, it's just exponentially decaying. If we've got this value of zeta between 0 and 1, we've got an underdamped system, so we have an imaginary component to the pole, so therefore there's going to be oscillatory components, but it's going to be decaying. So we have an exponential decay envelope on our oscillatory signals. If we've got no damping at all, then we've just purely got an oscillatory system. So we'd say that was marginally stable. And if we've got a positive value of a real part of S, then that means that we're going to get exponential growth. Therefore, the system is unstable. And you can depict this quite easily, just a little graph like this. We'd say that probably the first one you should put in is the critically damped. So your critically damped is going to be this sort of brown one. It goes up as fast as it can to the step value, but it doesn't overshoot at all, right? So there's no oscillatory component in there at all. It just goes straight as fast as it can up without overshooting. If it was more damped than that, and that's what this blue one, this is overdamped, it still doesn't oscillate, but it takes a lot longer to actually get to the asymptotic value of what the step should be. If it's underdamped, it means we do have oscillatory component in there, so it's basically going to be a damped oscillation. Depending on how damped it is, you won't get very many cycles. As you can see, this one's just rising up, overshooting, then coming down again, and a bit lower than basically settling out here. If there's no damping, then we've got a continuous oscillation of continuous constant amplitude.